Today we're going to go over the answers to quiz 4, and this quiz was around the concept of circuits and current and how circuits are put together. So let's take a look at this first problem. We have this circuit represented by 3 resistances and a power source, and it tells you the resistance for each resistor, 10, 15, and 5, and asks for the total equivalent resistance. Well, the first thing to answer this question, what you need to see is that this isn't currently in series. That is, there's only one path that the electrons can take, and so they're lined up serially along from the beginning of the source to the end. And the equivalent resistance in a series circuit is equal to the sum of the resistances in that circuit, however many there are. In this case, there are 3. So you have 10 plus 5 plus 15. So the total here is 30 ohms. So the equivalent resistance, or the answer to the first question, the equivalent resistance is 30 ohms. The second question says if the current, which is I, which is represents the flow of electrons, is 2 amps, and this is actually a mistake because the way this is written, the answer is actually 0.0 ohms. It has 3 significant figures. The current is 2 amperes. So what's the total voltage? Well, Ohm's law, if you need to look that up in your book, you can, states that the voltage is equal to the resistance times the amperage. And so in this case, the equivalent resistance, so the total voltage would be equal to the equivalent resistance times the total current. So the voltage here is going to equal 30 ohms times 2 amps, or 60.0 volts. And one way to think about this is, obviously the resistance is what is preventing the current from flowing, and the current is the amount of flow. And so the voltage represents the oomph, or the motivation, or not power is not the best word to use, but the amount of energy that's behind the flow of these electrons. And so the greater the resistance, the more oomph you need. The more flow, the more oomph you need. And these two would be related to each other. Now the next question says, what would the equivalent resistance be and total voltage if these were in parallel? So instead of what is currently drawn here, you have a parallel circuit, and a parallel circuit would look like this. You would have 3, and a parallel circuit, I've drawn it in such a way as it looks parallel, okay, but they don't always look that way. But the point is, when the flow gets to this point, it has a choice on which way it wants to go. And that's the difference. When you're on this one, there's no choice. You gotta go in one direction, which is why if you have light bulbs, some Christmas lights are lined up in series. And because of that, if one burns out, none of them work. And you have to go around and try to find which one's burned out. Well, in this case, because there's an alternative, if this one burns out, these two continue to go. But we know that the law is that 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so forth, however many resistors you have. So 1 over RE is going to equal, in this case, 1 over 10 plus 1 over 5 plus 1 over 15. And when you add fractions, now we're into math, you add fractions, you find the least common denominator, and the least common denominator here is 30. That is the smallest number that all 3 numbers will divide into and have a whole number. So 10 divides into 32 times, 5 divides into 36 times, and 15 divides into 3 times, 2 times. 10 divides into 33 times, 5 divides into 36 times, 15 divides into 32 times. If you add those three up, you get 11 over 30. Now that's not the answer, that's 1 over the answer. So the answer, RE, is this flipped over, or 30 over 11, and I think that works out to something like 2.88 ohms as the equivalent resistance. Again, you use this same equation. V is now going to equal 2.88 times 2, and so that's going to be 5.67 volts. So here, this is your equivalent resistance. And notice, because you've given the electrons various paths to take, the amount of oomph required is considerably less, okay? Because it doesn't have to push through all three of these at the same time. The amount of voltage required is significantly less. And that's one of the advantages to parallel circuitry. Okay. Let's move on to the second question. The second question here says, in the above circuit, what is the power used? Well, remember that power is equal to voltage times amps. And the above circuit here is the series one. So the voltage here is 30, and the amperage, no, the voltage we had, was 60, and the amperage was 2, and so the power is 120 watts. Or, and I'm doing this because of the next kilowatt guy, the power is 0.120 kilowatts. A kilowatt is 1,000 watts, so you would divide this by 1,000 to find the kilowatts. And so it says, if the circuit is run for an entire day, what is the total power used in kilowatt hours? Well, you just take this. If you use the original 120 watts times 24 hours, but then you'd have to divide all that by 1,000 watts in a kilowatt. And so, or you could just multiply this by 24. And if you do that, you get, let's see, 48 or 8. 48,042. Okay. I'm trying to make sure I got, yeah, that's right. 2.88 total kilowatts. And the kilowatt costs 15 cents, or $0.15 per kilowatt hour. So if you multiply this by 0.15 per kilowatt hour, the kilowatt hours cancel out, and you end up with about 43 cents, I think it works out. Or 43 cents in charge. So, going back up here, the power is V times I. Voltage was 60, I was 2. So that's 120 watts, or 0.12 kilowatts. So, the total power use in a day is going to be the number of watts times the hours of use. So this number without the 1,000 would be watt hours, but we said in kilowatt hours, so we're dividing by 1,000. So we end up with 2.88 kilowatt hours. And then it's 0.15 cents per kilowatt hour, so you multiply those two together and you get that.